Welcome to this section of the Knime tutorial. In the first video, you have seen like how the Knime pipelines is working and how they used to connect to different pipes here, then different nodes, and then to generate the reports. In this section, I'll be showing you how to use this Knime on Cheminformatics platform, like reading the SDF files, the chemical files, and performing some property calculations, converting into different molecule objects, and computing the Lipinski's rule of five, and learning some Java, learning some snippets, how to write snippets of code to do some filtering of molecules, how to cluster some of the molecules in the last this pipeline. And to start with, here you can see the Knime and the window. It contains the workflow projects here, this one, and also it gives access to the example projects. You need to just log in into the Knime, and it will just connect into the public Knime server, where it has like free workflows installed, and you just then need to just select one of them and then copy the absolute URL, and then you just come down and just Control V or Command V, just paste that into the local workspace, and the workflow will get into your local workspace here. So these are the example repositories here. These are the favorite nodes, what the most nodes you mostly use, and this is the node repository of what are the different connectors and the nodes which are available to do some data processing and analysis. It has like integrated with R. It has the Wake machine learning. It has some reporting tools. Has some community nodes based on the Cheminformatics tools like RDKit, the Earlwood Cheminformatics, then Humble ABI, the CDK. Also has the Chemaxon Marvin plugin to do some chemistry, like sketching structures and everything, and also has some inbuilt chemistry functionalities and nodes to do some Bayesian learning, doing some mining, and then some other miscellaneous extracting chemical structures, and also has some statistics also, and it has data manipulation and everything. It also connects to the databases where you want to connect your data, and then process that data, and then do some filtering of those data, maybe, so, or doing some analysis of that data. So yeah, here you go. So it's a very nice tool to build workflows in your when you are in your industry. Uh, to start, I'll show you here how to read your files, do some filtering, and make some plots, converting into different molecule objects, building the Java snippets, or writing some snippets of codes. First, to start with, is SDF reader. So if you want to search a node, or if you want to build a pipeline, so you need to search a node. So for example, this SDF reader can be searched using this. So here is this, the chemistry has this SDF reader, and you just need to double click it, and it gets popped out here. So since you have it already, and you don't need it, you just you can delete it. And if you want to change the name, you just read chemistry, something like that. And also you can just give annotations using the clickable workflow annotation. I can just change the background color, the fonts, and italics and everything. So that's how I colored here. Uh, you can also discard it, just if you don't want it. Yeah. So the start. So when you get the node, you need to configure the node every time. So first, you need to give the user since it's SDF reader, you need to give the file name here, and then in the property handling, just see the scan the molecules. What are the properties which are there in the SDF file, like molecular weight, formula, and Campbell ID? Just apply it, and then you can see it's on this amber light, which means it is kind of like ready. So there are three lights here. So one is like not red one. The first one is red, then the amber like little bit yellowish, and then the green light. So it's just a normal traffic signal light. It's not ready, stop, and then it's like kind of ready, and then just then after that green. So it's been processed by this node. Uh, uh, so here I just try to just configure it, and after that just so this reads the file, perform some Lipinski calculator, do some Lipinski property filtering, and then write the data on the SDF. Finally, write output the data. So for output, you can save it into the desktop here, or here, and then what properties do you want here to compute from this, and you can add more properties, and it will show on the final SDF file. So this is a meta node. Meta node is kind of, let's open the meta node. So the meta node is kind of a node which has like lots of nodes inside it. So you can have multiple nodes inside it to do uh, and merge it into a single node. So you can just do a right clicks and it will convert into collapse into a meta node. You can use that. So once I read the files, I need to convert into a chemical object. So there are like various tools for that, like CDK, RDKit, and Earlwood, Cheminformatics, Indigo. Those tools are used to convert into a molecule object. So after converting into a molecule object here, like the RDKit molecule, so you can just type in and then just see what the column name you want to give. Okay, I want to give the molecule object column name as RDKit mol object. So the molecule to RDKit mol object, and want to generate 2D coordinates, you can do that. It's up to you, or you don't want to do it, that's also fine. And then you can want to generate the descriptors. So you just type in your RDKit descriptor calculation, and this node will come up, pop up, and you just double click it and it will show it, and then drag a line from this node to this end node. So the RDKit descriptor calculation shows you what descriptors which are available. Or here you can see lots of descriptors here, but not the chemical fingerprints. So that has a different node here. So and also you just click it and then add, it will get added up here. So I want this four properties to get calculated, or maybe say number of rings, and then apply it, and then it changed. Then you want to do a row filter. Say for example, I want the compounds after computation, when you filter the compounds which have molecular weight less than 500. So the upper bound should be like 500, and the lower bound is nothing, it sets to any value like 0 or less than anything. So it calculates from this previous things, the Lipinski descriptors or something, and then after that you just give it here. So since I just configured here the Lipinski descriptors, so I need to remove it. So this is how, because these are the Lipinski's rule of 5. It's like less than 500, less than 5 log p, less than 500 molecular weight. Having one donors is less than 5, less than 10, and donor is like less than 5. Uh, then after that you do the log p filter the same way. You just select the column which you want to filter and select an upper bound, and then you just include the rows by attribute value. You don't want to exclude it or something, so you have to include. So what attribute you are selecting, you to include that. Same as the row filter works. So if you want to type a row filter, and you just type row uh, here is the node to do the row filtration. So you just double click it and you just give it here. That's it. And the same thing after that, after computation, the results will come out and collapse into a meta node. Just cross it, since it's already here in the Lipinski, and it will write it down here. So let's run it and let's see what does it say. Uh, so this is already is running and it got queued here because it was processing, and then it's already written here. So you can just type it. You can just see here. So it got saved into a sample file. You can just see it on. Uh, Simple to STF is saved already. Coming to the next pipeline here. This is very interesting pipeline. So let's do something on this and uh, so I want to print the molecule name, molecule, then chemical ID, salt strips. Okay. So it's getting executed. The same files, it's already in execution. And after this, if you want to execute everything, you just need to click this button. It will execute all the pipelines. If you want to select this one, select it, and then it will get computed on based on your selection and the nodes. See, all the things is done, all the things has passed, and then let's see what we do, what we are doing here. So first, we are reading the file. We are converting into the articulate molecule. Then we are stripping some molecules. The stripping molecules, I want to remove the salts from the molecules, which is not required. So I told you in the virtual screening, like we need to remove salts and everything. So here you can see the molecules. When once you open it, again I'm showing you. You just right click it and then molecules without salts. So I think all the molecules are without salts, uh, but still you remove those the 500 molecules, and then you can just maximize. Then just do some indigo, and then you can see the compounds. So they have different renderers. I mostly prefer indigo renderer. It is fairly cool. You can also do a Marvin rendering also. It's also fairly good and shows the chemical structures. RDK 2D depiction also. You can see the chemical structures, the molecules, molecular weight, and then the ID and everything. So after the stall stripping, I will calculate some descriptors. So these are the descriptors I want to calculate again the Lipinski descriptors. Uh, since I've already calculated it, so it's once you do it, and it will get just right click and you can see the descriptor files. Uh, and then just the radar plot gives the output shows you the radar based plots of the maximum limits of this. Uh, so you can see the Lipinski the values here. So what's the maximum and how does it this plots are behaving, and the compounds are behaving. It shows single lines. And also you can do a 2D scatter plot. So let's the 2D scatter plot looks like this, which is fairly interesting. And you just give the log p, and like then the molecule, and just right click. You can see the molecule by clicking it here and here and here. Just click it, and also you can just change like this, and you can set colors based on molecular weight or S log p, and like This is maximum the variable changing color and the size based molecular weight. So this is the sizing. There are some molecules like this which has high molecular weight and also has high log P. So this is the compound. Or you can just keep it like this way, molecular weight and the log. Yeah. So yeah, you can do readable plots, and with this you can just select. Just export as PNG the whole plot, and I can save it as PNG, or there are other SVG format. Uh, you can do box plots like this if you want. You can change the background color like this, and so this gives the molecular weight range, and then and once you normalize this, and it gives the range of this compounds and mean, median, and everything, and the lower bounds and the upper bounds and everything. If you understand what does the box plot does. Uh, so also there's another very beautiful plugin. It embeds the compounds in a 3D visualization platform called the Chess Mapper. So once you open the Chess Mapper, you just have to wait it. So it's embedding compounds in the three-dimensional space. So this is a kind of a free tool what the Chestnut people provide. So it embeds the compounds in 3D space. Only like they show some errors. To ignore for mapping and 480 as distinct 3D positions because it couldn't compute the 20 compound features. So once you're done with this, you can rotate it, and then it embeds using the PCA algorithm, and you can select the based on molecular weight. If you want to, just select, uh, and so you can use these two these two sets here. Just go here, and you can also select you can also visualize the compounds. This, and just select, and you can visualize the compounds. You can also use this, and if you go to this position, and you can just see the molecule. Yeah. Okay. This one is for this visualization. Coming to the next one, uh, and this one also does read the SD file and convert into the molecules, then calculate Lipinski descriptors, then convert the molecule into an indigo molecule, and then calculate some properties. So you want to configure it, what properties do you want to see, uh, and then convert into molecule to CDK, then does some Lipinski's rule of 5 filter at the end. So this is fairly simple. What you can do here, and you just need to execute it. Uh, Select, and reading the properties of it in the molecule properties. Once this is done, you can see the output data. Just right click data. Here you can just see it, the different properties just calculated, and I can do some clustering based on these properties quite easily and generate a nice report. And then you can just also just see the failures So these are the Lipinski. So there are like three things which didn't match. There are like many compounds. You can do a row filter which has using the upper bound, which has minimum zero, which has upper bound of zero. So all the compounds will get filtered out, which has like which is the count is like zero, like one or more features are not included. Uh, so this is a node which actually calculates it for you and just presents the results of the number of violations it need. But you can write it here like what I have written, writing creating a meta node and merge it into a single node. Uh, Now this thing does the k-means clustering here of this. So you read the file and let me open it. So it does it takes the input node and then computes generates the fingerprint. So the fingerprint it has different types of fingerprint. Now you're calculating clustering based on the fingerprint. If there are various types, you can see the RTKit provides its chemical toolkit, and then you're just missing the values. Okay, to do nothing with the missing values. Uh, if there is something you want to skip, so this node is there. And calculate a distinct matrix from this computed values. Then calculate the k meteorites of this and output the data here. And you might want to do a column filter, which has only the partition size. So actually it does the partition count. So if you want, you can want to partition it into 14 classes, and you want to partition it, so it actually partitions into 12. So now it computes the 14 one, and then this node passes the meteoroids and the size here. So the meteoroid, the compounds in the 14 compounds get passed here, and it does the constant filtration of this. Okay, I want only this things here, the partition size and the other properties, and I then pass it into this node. So you just close it, and then the node comes down here. Uh, uh, then you just keep these variables here, do some column filtration, then convert molecule into a data report, and then generate a report. So this pipe only shows the meteoroid molecules, and this column filter only shows the clusters which it belong and the distance and so on. So let's run this. In other platforms like Pipeline Pilot, it's very simple. Like once you create a meta node, you can save it into. You can create a folder here in Pipeline Pilot, which is a commercial program to do pipelining, and it has more features than normal what Knime has, and it has like inbuilt like all lots of not for pipelines, and it's very easy to compute or write scripts on Pipeline Pilot. But this is a very nice alternative to Pipeline Pilot. It's a free version of this pipelining. So, but it doesn't provide those meta converting, meta nodes. In future, maybe they might provide those sharing kind of tools where you can just save the meta nodes or save the workflow in particular in the node repositories, and so that you can share with the community pretty easily, or local sharing platform. So it's computed now, and let's see what does this show. You can see the view table report, and if you might want to consider into Indigo renderer, you can do that. Want to increase the size of the row and just see. Okay, this. So these are the compounds which belongs to this partition. These are the other things, the partitions which it belong, and so forth. This is how you they clustered, uh, and the distance from the medioids. This it's like this is normalized one. It's 0.86. Uh, and this report shows you the medioid values. The medioids, the partition 23, the 45. Partition size and the number of molecules is this one partition, and this is the medioid. There's another partition, 45 molecules. There's another one has 26, 23, and this is the other partition, and so on. So this is how you just do the medioids and do some clustering of the data. So I'll be coming out with a lot of other pipelines in future. So stay tuned for those pipelines. I hope you enjoyed the Knime workflow, this kind of tutorial. Just try it with your hands, download the pipelines, and just try to see how does it work, or uh, get hands on with this Knime workflow tools. Thank you.